Problem 6.24. You throw a 3 Newton rock vertically into the air from ground level. You observe that when it is 15 meters above the ground, it is traveling at 25 meters per second upward. Use the work energy theorem to find A, the rock's speed just as it left the ground, and B, its maximum height. Okay, so here we go. Here's the ground. And there's two states that we care about. So, state of the system is just the rock. First, it has initial velocity, and the height is ground level, 0. And then second, it's got some velocity, what was it, 25 meters per second, and a height, y1, y1, that's equal to 15 meters above ground. So think of this as the initial state of the rock, and here's a final state. Okay. What describes the initial state is going to be an initial kinetic energy. And then what describes the final state of the rock will be a final kinetic energy. Eventually, we'll be adding more to these ideas of initial state and final state. And the thing that gets us from one state to another is basically the influence of a force, and that force is gravity. So gravity acts on the rock as it's traveling upward. Gravity is trying to slow it down. It hasn't reached the maximum height yet, so it still has plenty of velocity and some height. And, I said this is the second velocity, or the second state, and then I put ones. All this means is, at a time t equals t0, we have an initial state, and at a time t equals t1, we have a final state. The problem doesn't make any mention of times whatsoever, but it's how you should think about it. It's these can't happen at the same time. It's the same system at two different times. So I just labeled these time t0, initial time t1. That's some intermediate time. I'll name t2 to be the time where the rock has its maximum height. But we'll get to that in a second. What are the forces acting on the rock? There's only one. So the free body diagram, or the force diagram of the rock, where this dot is the rock, and this is the only force acting on it, the force of gravity acting on the rock. So therefore, the total force on the rock is equal to negative W j hat. What is the displacement of the rock between these two states? I'll call the displacement vector S, and we're going up a distance y1 in the j hat direction. So the total work being equal to the change in kinetic energy, because that's the work energy theorem. So the work total is just the total force acting on the rock dotted into the displacement, since the force is constant. No integration needed, and I have negative w j hat dotted into y1 j hat. That's just equal to negative 3.00 newtons times, that was 15.0 meters, and then the j hat dot j hat is 1. So we get negative 45.0 newton meters, or negative 45.0 joules. So that's the total work done on the rock. The change in kinetic energy is final kinetic energy minus the initial kinetic energy, and it's the initial kinetic energy, or the initial velocity that we're looking for. That's equal to, I'll just call this work total for now, because I don't want to write out negative 45 all the time. And we're going to solve for this velocity. So I'll throw this whole term onto this side and move that term onto this side. I get m over 2 vf squared minus work total equals m over 2 v naught squared. Multiply both sides by 2 over m. So that these cancel, and then I can distribute that 2 over m, so that I have a vf squared minus 2 over m times w total equaling initial velocity squared. Then I'll square both sides, which gets rid of that. Now I'll put in the numbers. Actually, let me do one more thing. So that's the final velocity squared minus 2 over m, and then w total. What was w total? W total is negative w times y1. Or, there's too many w's. That's the weight of the rock. That w is the weight of the rock. And the weight of the rock is mg. So I have another cancellation of the masses. So maybe I didn't even need to... Oh, I never calculated the mass anyway, because I was only given the weight. The weight of the rock was 3.00 newtons. So that's 25.0 squared. 2 negatives makes that positive. 2 times 9.8 times 15. And my calculator says... So I'm going to do this first. 2 times 9.8 times 15 equals 294. Now I'll add 25 squared to that, 919, and take the square root of that, 30.314. 30.5 meters per second, or with the proper sig figs, 30.3 meters per second. Okay, now that was the answer to part A. Part B. Let's do it two ways, but I'll just stick to one way first. Let me preview the two ways. So now that I have the initial velocity v0, v0, and I'm gonna use this one with more significant figures in the calculation of the maximum height. And this is great for the answer, but I want to carry a few more significant figures just in case stuff. So initially, the rock had 0 height and a lot of speed. Now, and this is the initial state, but now we have a new final state where the rock at time t equals t2 has a velocity v2 equaling 0 because it's at its highest point, and y2 equaling something. So y2 means y at time 2. But instead of this initial state, I could have used the intermediate state. I could have used the state of the system at time t1, and then calculated the work gravity did to get this system to go from this state to the t2 state, this state. But let's stick to the way I drew it first. We'll do this, and then this. I don't know what I meant by the last sentence, so just forget what I said there. Okay. So let me redraw this and this. So we're looking for y2, the maximum height. The total work done in going from the initial state to the final state is going to be equal to the kinetic energy final minus the kinetic energy initial. Let me change that F to a 2. Kinetic energy at time 2. That's actually 0 because the velocity v2 is 0. So the kinetic energy, 1/2 m v2 squared, is 0. So on this side I just have 1/2 m v0 squared, which I know. I didn't calculate m, hopefully it drops out. And the work total, so the displacement vector is going to be y2 j hat in this case. And the total force, let me move this. the total force is going to be negative W J hat. The total work done on the rock is F total dotted into S. Negative W times Y2 times J hat dot J hat, which is just 1. So that's negative mg y2. So negative mg y2 is equal to negative 1/2 mv naught squared. So y2 is equal to negative m over 2 v naught squared divided by negative mg. And yep, the masses again cancel. We can cancel a negative sign. That's equal to v naught squared over 2g. And v naught is 30.3. What was it? 316? 315? 315 squared divided by 2 times 9.8. Divided by 2 divided by 9.8. 46.88775. So y2, the maximum height, is, with the proper sig figs, 46.9 meters. Okay, so that's the end of the problem. But let's redo that last calculation using that intermediate state. V1 was 25.0 meters per second. Y1 was 15.0 meters. So that's the initial state. The final state. I gotta do that so you know that that's ground. V2 is 0. Y2 is the thing we're trying to find out. So going between these, what's the work done between those two states? Now the displacement vector is y2 minus y1 j hat. The net, or the total force, that's still the same. That's still negative w j hat, or negative mg j hat. So the total work done between those two states is negative mg y2. Y2 is the thing we don't know. Y1 we do know. J hat dot j hat. I don't know why I keep writing that. That's pretty simple. Okay, so changing kinetic energy. The final kinetic energy is still 0. The initial kinetic energy, m over 2 v1 squared. And we're looking for y2, so let's pause and just look for this distance first, the y2 minus y1. Y2 minus y1 is equal to negative m over 2 v1 squared divided by negative mg. As luck would have it, the negative m's cancel. And now we can find y2 is equal to y1 plus v1 squared over 2g. So that's 15.0 meters plus 25.0 squared over 2 times 9.8. Let's forget about that unit for the moment. This better come out. 25 squared divided by 2 divided by 9.8 equals 31 point something something plus 15. Did I do this right? Did I mess something up? That was 15, yeah? What happened? 25 squared divided by 2 divided by 9.8 plus 15. I get 46.88. 46.9 meters. Is that? Oh, sorry. For some reason I thought the answer was 40.9 or something. Yeah. It's the same thing. As it should have been. Ugh. I was doubting myself. My pen doesn't register when I get close to the edge of the screen, so that's why it's weird. 46.99 or 46.9. Anyway. There you go.